phase of the course, which is different kinds of PDEs. Okay, parabolic we'll start with. So we all know this. Many of you are actually doing research where you solve time-dependent problems or unsteady problems. Okay, this is something that we are often interested in because we are interested in the history of how things change with time. Okay, not just the steady-state solution. In fact, there are many problems in real life which do not even have steady-state solution. Okay, the solution is inherently unsteady, and so you have to compute it as an unsteady problem. Okay. So there are two ways to obtain the steady-state solution. One way is to, so suppose I take a heat conduction equation. Okay, so this is your unsteady transient term, storage term. This is your conduction term. Okay, you can solve the steady-state problem two different ways. One is to simply say, okay, steady state means that's equal to 0, so I'm going to solve just the steady state equation. Okay. Another approach would be to time march this equation such that you go to time t equal to t infinity or very large time and you get the steady state solution. Okay. Both are valid approaches and both are used extensively in numerical computations. Now there are pros and cons to doing it one way or the other. Okay. One of the biggest advantages of time marching is that there are many problems where you don't know a priori if a steady state solution exists or not. Okay. In such a case, if you try to compute the steady state solution using an equation like that, the steady state version of the equation, you will find your code is never converging. Okay. Classic example would be, let's say, a natural convection problem. Okay. So if you're doing, let's say, fluid flow over a hot plate, okay, there is no steady state solution at high enough Rayleigh numbers for that problem, because what happens is at one instant of time you have a plume rising here, another instant of time you have a plume rising there. Okay, so if you take snapshots at different instances of time, even when the system has so-called gone for hours and hours, you'll find that it's still changing. Okay, it doesn't even have a steady state solution. So in such a case, if you try to solve the steady state equations, you run into problems. So that's one big advantage of time marching methods. You can actually find out if there is a steady state solution or not to the problem. Okay. Now, if the steady state solution is of interest, so now we are talking about time marching. Okay, so time marching this equation to steady state. So we're saying if we are only interested in the solution to this part, okay, the steady state solution, then we can literally use, or we can arbitrarily use values of k, rho, and Cp that will allow us to get to steady state fast. Okay, so I don't have to use the real values of rho, k, and Cp to get to steady state. I can choose arbitrary values that will take me to steady state quickly, because you know these values don't affect, as you can see from the steady state governing equation, doesn't affect the steady state solution. It's independent of that. Okay. So therefore, I can choose these values in such a way that I get to steady state quickly, which means I have to go fewer time steps. Okay, and people often do that because they realize that I'm not interested in the intermediate solutions, and the steady state solution doesn't depend on those properties. So therefore, I can use arbitrary properties. Okay. So that's what I'm saying here. But if you're interested in the unsteady solution, then of course you have to use the actual properties. All right. In either case, the time derivative must be discretized, and that's what we are going to talk about today. Discretization of this term. Okay. So I've just written it in a different way where I've divided through. So if you take, for example, the heat equation, okay, I've divided through by rho Cp. So this quantity is called the diffusivity. Okay, in the case of the heat equation, it's called the thermal diffusivity. All right. It's always a positive constant. That's the only thing to remember about it. There's nothing else that matters as far as the numerical treatment is concerned. Okay. All right. Now, to solve this equation, in addition to the boundary conditions that we have for x and y, which you've been doing in your homework, we also need initial conditions. Okay. So the initial condition can be a function of x and y. Okay, it doesn't have to be a constant. It can be a function of x and y. It's just some solution you're starting with. So what we are going to do is now apply our age-old Taylor series expansion to derive these time derivatives. Okay, same idea. So now what we are doing is, instead of spatial nodes, we are introducing temporal nodes, nodes in time. Okay, and we are going to use a time index n such that t is equal to n delta t. So when n is equal to 0, that indicates our initial condition, starting point. Okay, and t is equal to 0 at that time index. And then we go, in this case we are using equal time steps, but you don't always have to do that. It's the same thing with space. We've been doing most of our derivations with equal delta x, delta y, but doesn't have to be always like that. Okay, so if we take this Taylor series expansion, so we are expanding a future time, okay, in terms of, or you can say we are expanding the present time in terms of an old time. Okay, either way you can interpret it. Typically we think of n as old and n plus 1 as current. Okay, that's the language that people use instead of saying future and present. So current or present and old. All right. So if we rearrange this, we get that. All right, and clearly you can see if we approximate it as that, then our error is of order delta t, first order in time. Okay. So here's our governing equation. We now plug it in, the expression that we just derived, and we get that. Okay. Now, since we derived dt dn, if you look at this expression here, we derived dphi dt at n, at the old time step, okay, or the old time index. Therefore, on the right hand side, we also should use old values here everywhere to be consistent. Okay, and the errors, associated truncation errors, are delta t, delta x squared, delta y squared. Second order in space, first order in time. All right. So that's our governing nodal equation. And we can rearrange that to write it in this manner. Okay. So what I've done here is I have put everything with index n on the right hand side and everything with index n plus 1 on the left hand side. So we are trying to calculate present time step values based on old time step values. Why? Because old time step values represent initial conditions that are known. Okay, and therefore we can calculate this guy from the old time step values. Okay, so I just mentioned these, that everything on the right hand side is known because these are initial conditions. So if I start with n equal to 0, then these are my initial conditions that I have set to start off with. Okay. Now, one thing I want to emphasize here is that when you do iterative solution, you also start with, you can call it initial condition, but really what it is an initial guess. Okay. Here it appears that it's almost the same idea. You're starting with some initial value field for phi. Okay. But in this case, this is the actual physical condition. It's not a guess. All right. When you're solving steady state equations and you start with an initial guess, you've already noticed that the final solution doesn't depend on the initial guess, as it should be. Okay. But here it's a completely different story. Your time dependent solution will actually depend on what initial condition you set. Okay. Maybe the steady state solution will not depend on that, but the intermediate time solutions will depend on what initial condition you set. Okay. So I guess the basic difference is that when we do steady state solutions, we are not interested in intermediate solutions ever. We are only interested in the converged solution. Okay, so if you draw an analogy to that, here in contrast, we are interested in the intermediate time solutions if you're looking to solve an unsteady problem. So pictorially, this is how you best represent what's happening in the explicit method. So think of it this way. Here is my time plane n. Okay, so I'm now thinking of x, y, okay, my mesh, and then I'm thinking of time in the third direction. Okay, so here's my time index n. You can think of n equal to 0. That's your initial condition. All these values are known. Okay, from that, according to this formula here, we are using all these values to calculate the value at a new time plane, which is pictorially represented by this guy. Okay, so calculation of this guy requires all these values, all five actually. Okay, but notice that it doesn't require any other value on this plane. It only requires old values. Okay, so that is why this method is known as an explicit method, because this formula is an explicit formula. You don't need any solution of simultaneous equations. Okay? It's kind of like the Jacobi method where everything was treated explicitly. All right? So here on the right-hand side, everything is known, and that's why it's known as an explicit method. The other name for it is the forward Euler method, and that's because here we are expanding, going forward in time, okay, using an expansion about an old time. All right? You will see later on that you can do it the other way around. You can do n about n plus 1 also. Okay? So those are the two, that's why the two names that are used for this method, explicit or forward Euler. Okay? Any questions? Many of you are probably familiar with this method. It's probably the most simple of all kinds of time marching methods that are available there. So here is the summary of the algorithm. So first step is you set up initial conditions for all nodes. Okay. So this is basically starting at n equal to 0. This is very similar to starting with an initial guess in an iterative method. Okay. You get all nodal values at the next time step. You compute phi I plus I comma j at n plus 1 using your explicit update formula. Then you reset your initial condition, and you proceed to the next time step and repeat steps 2 and 3. Okay. So the advantage is it does not require any matrix inversion. So therefore the computational cost and memory is very low. And it's very easy to set up and use. Okay, and in fact, if you look at this, there is an extremely strong analogy with the Jacobi method, because in the Jacobi method, this is exactly what you do. You start with an initial guess, you apply an explicit formula, and then basically this reset of initial condition simply means that you're updating the value of phi. Okay, and then you're moving on until convergence happens, and in this case, you are proceeding to the next time step until you think I have gone so many time steps, or until you get steady state solution, let's say. Okay, that's basically the idea. So there is a strong analogy there between time stepping and the Jacobi method, time stepping using the explicit forward Euler method. Okay, so these are the advantages, of course, and in fact these explicit methods, although not the first order Euler, but other explicit methods are very popular in many computational areas. For example, when people do DNS of turbulence, typically they use explicit methods because storing the matrix and solving a set of simultaneous equations is a big headache when you have large number of mesh points, as we've seen. Okay. But this one here doesn't require any matrix inversion, which is kind of unique. I mean, if you think about it, I'm starting with an old solution. I keep time marching, okay, and then I get to steady state. I didn't have to invert any matrix, nothing. Okay, so it's kind of nice in that regard. But there are some problems, okay, and the problem being the time step size has some restrictions. Okay. And to figure out what those restrictions are, we are going to now do a stability analysis of the method. All right? Any questions so far? Okay, so for the stability analysis, I'm going to just look at the 1D equation, because we are really interested in instability associated with this term, not instability associated with whatever is in there. Okay? And also, to remove any kind of instability associated with iterations, I'm just treating this as a one-dimensional problem in space, so that you don't have to worry about iteratively solving anything, because later on we will compare this to an implicit method, where if you do 2D, then you have time stepping and iteration within time steps. Okay, because you won't be able to use a direct solver for solving the set of equations. So to avoid that, to make apples to apples comparison both for explicit method and implicit method, we're just going to take the 1D case, okay, where there are no instabilities associated with iteration in space at all. Okay. So if we do that, then here's our equation. Just taken the y derivative out, and just like for iterative methods, we said, okay, we can have an exact numerical solution that satisfies this equation. Now what you can think of, in this case, the exact numerical solution may be one that you got. So think of it this way. Suppose you time march your solution by one time step, delta t, okay, using this formula. So then you have one solution for that guy. Okay, you perform now the same calculation and get a value for this guy, but using, let's say, an infinitesimally small time step, very, very small time steps, so that there are no errors associated with time marching at all. Okay, so maybe you take 1 million tiny time steps which take you to delta t. Okay, that's what we are calling the exact numerical solution to that equation. All right, very, very small time steps. So the only error in this equation here is associated with your truncation error in space. Okay, so when you subtract out these two solutions, basically what happens is the truncation error due to space cancels out, and all you're left with is an error that you have due to time marching. So that's your starting point. So you're starting with some error distribution. And then the next question we are asking is, does that error distribution that we have, does it grow with time or does it decay with time? Okay, so that's basically the idea we are exploring here. So we have an error equation which looks like that by subtracting out this guy from that guy. Okay, and now we are going to ask the question if that error decays with time or grows with time. Okay, so just like before, we are going to represent the error by a Fourier series. Okay, so now here, this is error at node j and time index n. Okay, notice that now the amplitude also has a time index n. So that's the amplitude at time index n. Okay, now if that amplitude at index n plus 1 becomes larger, then we are in trouble. Okay, because it will successively keep growing with more time marching and finally blow up. All right, so very similar idea as what we did for iterative methods, except instead of a iteration index, we are now using a time index. Okay, so that's the definition of those two quantities. So I'm saying here that in our earlier studies for steady state problems, we considered an amplitude that grew or decayed with iteration index k. In this case, we are looking at a 1D problem in space, which implies that when we do the implicit method, we will do a direct solver. So there is no growth or decay of the amplitude due to iterations. It's only due to time marching. Okay, so that's basically the idea. Now, what people do is, and this is just again to simplify the math and make it more elegant, is they say that, okay, the amplitude, we are going to write it as e to the power beta mt, okay, where beta m, and of course t can be written as n delta t, and beta m is a complex number. Okay, such that, so now if you take that, you can split it up into a real part and an imaginary part. Okay? And if you now write these two components separately, you get something which looks like that and then something which looks like that. The reason I'm writing it that way is to show that this part grows or decays with time. This part is oscillatory in nature because it's e to the power minus I theta, which is cosine theta plus I sine theta. That's oscillatory. Okay? And then this is really the amplitude that can grow or decay with time. It's kind of like writing constant times exponential of I theta. Okay, so this guy can grow or decay with time, the amplitude, and this guy is oscillatory. Okay, so just another way of writing the amplitude so that we have a time wave here. Okay, and then we also have the amplitude showing up there. So when we do that, then instead of AMN, we can write it as that. Right? And further, if we denote the power beta m delta t as xi m, okay, then we can write that as xi m. Now notice, I should clarify here, this here is not a superscript that denotes time index. It is actually xi m to the power n. Okay? Because you see here, this is what we have. E to the power beta m delta t is xi m, so therefore this is xi m to the power n. Okay? Even though it looks like just a superscript denoting time index, it is not a superscript denoting time index. It is actually to the power n. Okay? So make a note of that just so that it doesn't confuse you when you go through the derivation. Any questions? So that is different from what we had here, where this guy represents just amplitude at time index n. Okay? But by the time we get to the next slide where we have made this substitution, we are actually looking at xi m to the power n. Okay? All right. The nice thing about writing it this way is as follows, that if you plug in t equal to 0, okay, then you can clearly see xi m to the power 0 is equal to 1. So what we are doing is we have sort of normalized the amplitude, and we're saying, okay, our starting amplitude is 1. Does it grow from 1 or does it decay from 1? Okay, does it become greater than 1 or does it become a fraction? Next time step. Okay. Instead of having to calculate amplitude ratios, we have normalized everything, starting with 1. All right. So therefore, it is clear that if the magnitude of xi m is less than 1 in the future time step, then the error will decay, and if not, then it will grow. Okay. So this criterion for stability is that the magnitude of xi m must be less than or equal to 1, or this. Okay, that's your criteria for stability for time marching methods. Okay, so let's start with our error equation. That was our error equation. We are now going to plug in our Fourier series, just like we did for standard iterative methods. Okay, so before we do that, we are going to make a couple of adjustments. One is we will choose our central node as j equal to 0, and then we'll use a +1 on the right, -1 on the left, just like we did earlier. Okay, and we'll also get rid of the summation because we know the Fourier modes are all linearly independent, so we'll just skip a couple of steps there, get rid of the summation. Our error is given by that. Okay, so again, I've gotten rid of the summation. This is actually summation over m modes, m going from 0 to infinity of that, but for simplicity, we are getting rid of that. Okay, so that's our error. So therefore, if you now look at the one-dimensional case, this is j equal to 0, j equal to +1, j equal to -1. Okay, so here I have xi to the power 0 times e to the power 0, which is e to the power 0. Xi to the power 0 is 1. Okay. Here I have e to the power plus I theta, because again I get 1 times e to the power plus I theta. Okay, and here I get e to the power minus I theta, 1 times that. In the next time step, my n is equal to 1, so I get xi to the power 1, and that's what you see here. Okay, xi times exponential of 0. Okay, so this kind of a figure is helpful in understanding what the different terms become in the error expression. All right, so now we plug all that in. So here was our original error expression. So this guy simply becomes a xi times exponential of 0, as you saw in the picture, okay, which is nothing but that, xi. And then you have an exponential of 0, which is 1. And then on the right, you have e to the power plus I theta plus e to the power minus I theta minus 2. So that 2 is basically 2 times exponential of 0. Okay. So if I simplify that, now it becomes that. The sign terms cancel out. Okay. Everybody with me? All right. Now we are going to use this relationship. 1 minus cosine theta is 2 sine squared theta over 2. And so therefore my xi becomes that when I use that. Okay. Stability criterion is that. Okay. So therefore, if I take my xi and plug it in there, that's the inequality it has to satisfy. Okay. Now this guy here is always greater than 0, always positive, because sine square is always positive, and of course alpha, delta t, delta x squared, they're all positive quantities. Okay. And that's the reason we use this identity, because we wanted to get a sine square here so we can clearly say this is positive or negative. Okay, if I keep the cosine around, it's hard to say if it's positive or negative. All right. So this is always positive, and therefore irrespective of the value of theta, this is always true. Okay, if you subtract a positive quantity from 1, it's always less than 1. All right. So upper bound, this part here of the inequality, is satisfied no matter what the value of delta t, theta, delta x, any combination you give me, it's always satisfied. All right. We now look at the lower bound. Lower bound should satisfy this criterion, and that yields that relationship. Okay, so just a little bit of algebra, which we can further rearrange to get that. Okay. Now we are looking at the worst case scenario. The worst case scenario, okay, so we are looking for a constraint for delta t. Delta t. So if, for example, let's say sine square is very close to 0, then it will give me a very large number on the right hand side. And so it will say, okay, my delta t can be as large as possible up to that point. Okay. But if sine squared theta is very close to 1 or exactly equal to 1, then I get the minimum possible delta t, the tightest constraint. Okay. So that's our worst case scenario. So the worst case scenario happens when sine squared theta is equal to 1. Okay. And that gives us a delta t max, which is delta x squared over 2 alpha. All right. So this is the stability criteria for the criterion for the explicit method, explicit or forward Euler method in 1D. All right. This is what it's called sometimes. Okay. Now, does anybody know there's this non-dimensional number? Of course, it's a non-dimensional number. As you can see, we are comparing it to a number that has a name. Anybody know the name? For those of you who have taken heat transfer classes, alpha T over L squared. Anyone remember what that is? No. It's called the Fourier number. Okay, so this here is called, so Fourier number is denoted by, typically in heat transfer books, they either call it the Fourier number or they just write it as T star, non-dimensional time. Okay, this is alpha T over L square. L is some characteristic length. So if you go back to one-dimensional heat conduction in a slab, okay, you will see that. This here is simply called the grid Fourier number. All right, because it's using delta t and delta x instead of t and x or t and L. It's based on the grid spacing. That's all it is. Okay, but it's a non-dimensional number. So the stability constraint is that the grid Fourier number must be less than half in 1D. Okay. So basically it says that as long as you use a time step less than the delta t max, then you'll be fine. The error will not grow with time. Okay, it will just stay as is. Otherwise, it'll blow up. Okay, I want to show you a little example here of what happens when you violate the criterion and what happens when you obey it. Sorry, seems to have frozen for some reason. Okay, so here is a little example. Okay, so let me try to make this a little larger so you can see it clearly. So this is the equation we are solving right here. Okay, and the initial conditions are, so the boundary conditions are this. The boundary conditions in this case are actually time dependent. Okay, so we are solving it in 0 to pi. These are the two boundary conditions at the two ends. And then the initial condition is a cosine distribution. So we're starting with a cosine wave, okay, as our initial condition. And I'm using 21 grid points, 21 nodes, okay. And what I've done here is I've done computations using two different time steps, okay. This one uses 0.8 delta T max. So whatever is the delta T max prescribed by the stability criterion, this one uses 80% of that. Okay. And what you see here is, so now I'm going forward in time, 1.6 delta T max, 9.6 delta T max, and so forth. So these are just increasing time this way. Okay. And here is what happens to the solution. Okay. Now when you go, this one here is done with 1.6 delta T max, which is clearly a violation, okay, because obviously the maximum we can use is delta T max, but we're using 1.6 times that, okay. And what you notice is that it doesn't blow up right away, okay. You see 1.6, 9.6, 17.6, the solution still looks meaningful and pretty close to what you see here. But after a while, the errors accumulate enough that it blows up. Okay, so this is something to be cautious of, that when you exceed the stability criterion, especially when you exceed it by a relatively small amount. Okay, now of course, if you use 10 times delta T max, it will immediately blow up. Okay, but if you exceed it by a small amount, you won't immediately see the solution blow up. Okay, it might take a while, and you might be thinking, well, does that mean my stability criterion is just garbage? Okay, the answer is no, it is not garbage. It's just, you know, the errors are accumulating slowly, and at some point it will blow up if you go far enough in time. Okay, here's a little plot I wanted to show you down below. So what I've done here is I'm looking at the error. So this is between the analytical solution and the numerical solution, the actual error. Okay, that error, by the way, has both temporal error, discretization error, as well as error due to spatial discretization. Okay, the delta x square and the delta t. Okay, so what this is showing you is, of course, at time t equal to 0, you have 0 error because you're starting with the initial condition. Then, as you go forward in time, the error goes up. Okay, but what you see is that with time, if you're using a small enough delta t, this error just stays almost constant. It's actually going down a little bit because as you go towards steady state, your time derivative becomes 0, and so the temporal error basically goes away completely. So it is asymptoting to a point where you have only spatial discretization errors. Okay, but the important thing to note is that with time, this error is not growing anymore. It's staying put. Not that there is no error. There is error. Okay, we have the discretization errors, but due to time marching, error is not growing. It's just staying stable. Because we're saying every time step we are using delta t as our time step. So therefore, there is no reason for the order of magnitude of the error to either grow or decay. It should be order delta x square and order delta t at every time step. Okay, and that's what this is showing. This is basically the error at the 5th node that I'm plotting here versus time. Okay, so it stays pretty constant, but when you look at the other case where I violate the stability criterion, you see it goes up and then it wiggles a little bit and then it just goes away after some time. Okay, and that's instability due to the time marching alone, nothing else that caused it to blow up. Okay, everybody understand this? The behavior of the error. So, often I have confusing questions or confusing students getting confused that, okay, I mean, what exactly is happening? What exactly is expected of the error? Well, what is expected is for it to stay in the same ballpark all the time. Okay, you're starting with some error, which is truncation error due to discretization in space and due to time. That error should not grow because of the way you are solving the time-dependent problem. It should just stay put. Okay? All right, so let's go and go back to our stability analysis here. Any questions on that? So that's our stability analysis. Now, one other thing that happens with the stability analysis is that once the solution starts blowing up, you get unphysical results. Okay? So, for example, what you will find is, let me just give you another simple example here. So, suppose I solve a problem where let's say I have a 3-node problem, okay, and I'm doing a heat transfer calculation. These two are boundary nodes whose temperatures are that, okay, and this one I'm starting with an initial condition of 200 Kelvin. Okay, so now I'm going to advance forward in time, and what I expect is that next time step the temperature of this guy is going to be somewhere between 200 and 300, and slowly it's going to go up to 300, and 300 is my steady state solution everywhere, right? This is a simple heat conduction problem. That's what I expect. Okay, now let's see what happens when we do that. So we have T n plus 1 is equal to Tn plus alpha delta T over delta x square times Tn, so these are at node I plus 1 plus Tn at I minus 1 minus 2 Tn. Okay, that's our formula, explicit formula. So I'm going to plug in all the numbers. Ti at n is 200. Okay, and we'll leave it as that. I'll just write it as the Fourier number. And then here I have 300 plus 300 minus 2 times 200, which is 400. So I get 200 plus Fourier number times 200. Okay, So now what's happening, you can clearly see if I plug in Fourier number greater than 1, my temperature is going to be 400 or even greater than half. Okay, the moment I exceed half, so let's say I use 3/4 for this, that's going to give me a temperature of 350, which means that in the next time step, this guy has reached a temperature of 350, which is physically impossible. You can't get that by the second law of thermodynamics. That temperature can never exceed 300 Kelvin. It's an unphysical solution. Okay? You're getting that simply because of your numerical scheme, which causes this problem. And you can see, as long as I plug in half or less for that guy, I'm bounded between 200 and 300. I have a physically meaningful solution. Okay? It doesn't say that the solution is accurate necessarily. That will, of course, depend on what value exactly I use, what the value of delta T I use. Okay? But it is a stable solution and a physically meaningful solution. Okay? Everybody understand that? So there are implications on the physical meaning of the solution too when it comes to violation of the stability criterion. Okay, so let's move on. As I said, it leads to unphysical solutions and or solution blow up. Okay, and that may not always happen immediately. The error has to accumulate to some degree before it happens. Depends on the problem at hand. If you do a 2D calculation, then this is your stability criterion. Okay, so now the delta x and delta y both show up in your expression. And if you use equal delta x and delta y, then basically you can see here you get a 2 here. So basically delta T max becomes less than or equal to 1/4 for equal delta x and delta y. Okay, or sorry, this is actually, there's an alpha delta x square also. Okay, but instead of a half, you get a 1/4. All right. Now, one of the important things to understand here is that this means that if you, let's say, like you're doing your computations, okay, so you have 81 by 81 mesh and 41 by 41. So when you go from 41 to 41 by 41 to 81 by 81, you are having these two guys, which means your delta T will go down by a factor of 4 according to the stability constraint. Okay, which is kind of like a double whammy, because already you have 4 times more grid points, and now you are having to use 4 times less time step size. Okay, so total of factor of 16. Again, strong analogy with what you've been doing. Remember that factor of 16 you are getting in terms of convergence, 4 times number of iterations for the 81 by 81 mesh compared to 41 by 41 approximately. Okay, with doubling of the number of mesh points. Similar thing happening here. Okay. Now, if you really think of this, all of this has to do with how these waves are growing or decaying. Okay, it has to do with basically the spectral components of the errors, and that's why the behavior is very similar whether you are time marching or whether you are doing iterative solution. Okay, approximately a factor of 16 increase in the computational time when you half the mesh size in 2D. So because of this reason, even though explicit time stepping is easy to use, computationally cheap, you know, in terms of memory also it's very cheap, it is sometimes prohibitive to use. Okay. Now, one big problem with practical computations is, in practical computations, you are never going to use equal delta x and equal delta y, very rarely. So suppose you are doing a fluid flow computation, you'll have really tiny cells in your boundary layer, and that will coarsen out as you go out of the boundary layer. Okay, but your delta T will be restricted by the smallest delta x. Okay, so maybe the largest delta x in your computational domain allows a delta T of 1 second, but the smallest cell will allow a delta T of 1 microsecond. Okay, And so you have to time march at 1 microsecond. And good luck with that. Sometimes what will happen is you'll find that, well, for me to capture all the physics and really compare it to, let's say, experimental data, I have to run this simulation for about a second. And you find I'm taking time steps of 1 microsecond. Okay? So that's a big problem because of this time step constraint. Okay? And that's why people like to use implicit methods, which is what we are going to talk about in the next class. Now, one thing I want to caution you is that the error in the solution finally ultimately depends on what delta t you are using. Okay. Now, the fact that, let's say, we go to implicit method and we don't have a constraint like this, we can use any large time step we want, doesn't mean that that's necessarily a accurate solution. Okay. So keep that in mind, that the accuracy depends on the size of delta t. In this case, we have an additional constraint that we have to follow this stability criterion also. Okay. Any questions?